I'm going to be discussing about a very simple logic design problem or a logic design example. Uh, you may be familiar with the RTL logic design. Um, uh, this uh, this lecture is intended for um, college students or university students or who are starting out in logic design. Nevertheless, if you are experienced, you can leave me a comment and feedback. This is a very basic code of a arbitration logic, a very simple round robin arbiter. So let's look at that. Let's define the problem statement. So we have a few agents who are requesting to get access of a memory, for example, or it could be anything like nowadays you're hearing about the AI accelerator development. And in all those applications, you have multiple agents who are trying to get access to a resource that can be a memory controller unit or that can be a bus access. In all those situations, since you have one resource or two resource and the requesters are many, you may need some sort of a arbitration logic there. So for simplicity here, I'm assuming that there are four requesters. They are trying to get access to the same bus or memory management unit or your memory controller, which then pass on the request uh, to access the resource, right? So if you have many requesters, so which one you would give a grant? Okay, so in this example, I'm assuming a very simple round robin, which means requester one gets request, it gets a grant if no other requester is requesting. But it may happen that you have all four of the requesters are trying to access the memory at the same time in the same clock cycle. Then a simple program would help uh, to determine which one should get an access, right? So if the requester first got an access, then requester first should not get an access until or unless all other requesters got the access. Otherwise, requester one will keep on getting the access and other requesters will starve. So there are many algorithms, very efficient algorithms as well. But to explain the logic design, how to approach and how to code with a very simple example, I have created this. Leave me your comments, feedback, and any other topic you may want to discuss. So let's look at that for requesters. So first approach for any logic design, we have to keep in mind that um, if it is not purely combinatorial logic, then we may need to have a storage element, which means either state registers, if you are developing in a state machine, or simple registers to hold the state of the variables. And then your combinatorial logic, which is your, you can think of it as a arithmetic or unit or decision-making unit, right, which is going to work in the same cycle. So your combinatorial logic is supposed to execute in the same cycle. Your sequential logic is supposed to store the state of the logic. Very simple. Okay. So for requesters, and which one you would give a grant. And we think of some combinatorial logic and some sort of a register. Here I'm calling to store this register as previous grant register, which means that if the requester one got an access, so this register will hold the state that, okay, I have given the requester one to access. That means that if the requester one comes again along with the other requesters, requester 1 should not get an access. So to hold that state, I'm using this register. All right. And then this register gets feedback into the combo loop, and combo loop also gets, provide the input to the register. So let's again think in a very simplistic way, what can we do? So let's say, let's put all the requests into a variable, 4-bit variable, and then the grant into a 4-bit variable. Okay. So here, no other requester is getting a request other than the requester first. So requester first wants to get an access. So we give a grant to the requester first. Okay. Now what happens if the requester first and second, they come together, then since the requester first got an access, it should not get a grant. So we should get a grant to the requester second. In similar way, third, then first 2 requesters should not get a grant until we complete the full cycle. All right. So requester 4th and then first 3 should not get a grant. All right. So this is a simplistic, thinking behind the logic. All right. So what can we do? Okay. So we need to have some sort of a masking criteria that, okay, with this request, if we create another variable called mask, then mask all the requests coming in and then provide a grant. Okay. So for example, let's create a mask variable here. Initially, everyone is allowed. So we get a request 1, and then if we mask it, means the AND operation between mask variable and the request, we get a grant. Okay. And we get a grant here. And the other variable I'm calling a previous grant, which will feed to the D input of the previous grant flop here, that the previous grant was nothing. So now we have given a grant to the requester first. So previous grant will have the value 1. Okay. This could, you can think of a one-hot register here. Now, once we have understood it, what exactly is the problem and how to approach it. Now let's look at one example here, and another example that the grant will go to the second and then the previous grant will go to the second bit. Now let's look at the Verilog, a very simple Verilog RTL code. And I would explain that if you are a new designer, how you can organize your code. Okay. What is a good practice? All right, so let's jump onto the code. I have created here code for you. Let's say sure, Arbiter. Okay, so if you can see here, the line number 8, I'm calling all the common functions in a package file, common type, defs, and all. Okay. So I'm opening up the package file here in parallel. All right, so I have defined here in the package file. All right. So let's look at the code here. So I'm saying number of requesters are 4. Input, which is a type. I have defined a type that request, grant, and then the clock reset type, right? So you see your input output list is short. So tomorrow, if you have to add on 1 or 2 more signals, you just update the package and you don't have to add it in multiple files. It's a very good way to keep common elements in a package and then reference the package in the code. And here we are creating a flip-flop grant underscore ff for storing the previous grant. So I have defined the ff as a flip-flop defined in a package file. We'll show you in a minute. So we define the flop, and then we define a function, function which gonna do a combinatorial logic, So function accepts the request and the previous grant, and it will give you the grant. And then now once we have the grant variable, we just map the grant variable to the outputs. Very simple logic. Once again, just putting it through, giving you a minute or so to really look through the code. Very simple code, very clean code. All right. Now, let me close this file and let's look at the HR package file. So this package, you can put a bunch of things here. You can put if def for calling the package, right? That helps in compilation when you have EDA flow setup. Nevertheless, the important items here at line number 15, where you have, I'm defining the 4 arbiters, 1, 2, 3, 4, as a type T, just for simplicity. And the clock reset type I have defined here as well, clock reset. This is actually very good, useful thing to define clock reset at line number 16, because you say in modern SOC designs, you have multiple clock domains, right? So once you have a type defined, clock reset underscore T, you can just say clock 1, clock 2, clock 3, and that is kind of a strict typing, or when you compile it, it's very easy to see through the signals are going from which clock to which clock, and very easy to down the line fix the CDC issues in your code, right? So normally people don't, but I prefer that start practicing defining common signals and packages. So this also tells you, line number 16, that this clock is associated with this reset, right? So you can have multiple reset, you can have multiple clocks. So you can assign that which clock belongs to the which reset and whatnot. Is very helpful, right? Then the line number 18, 19, 20, this was for the FIFO common signals, which I was explaining in the previous example. In a previous lecture, you may look at the LeProFesseUR channel for other lectures. You may also look at my website, leprofesseur.org. So common codes I am putting there. So this code will also be there, and you can take a reference from that website, leprofesseur.org. Okay, so for the flip-flop, I have defined 2 kinds of flip-flop. One is without explicit reset, one is without with explicit reset. Both will create flip-flops. The way synthesize tool will create so flop at line number 24 and flop at line 25. Line number 25 flops have explicit reset, and usually I prefer to use those flops for the state registers. I want to have all my states get cleared as soon as the reset is deasserted, or reset is asserted, right? And the reset synchronization is with respect to the clock. The assertion of the reset is synchronized with respect to the clock, not the assertion. In the example at line number 24, the flop is created in a synchronous way, and the footprint of the flop will be smaller compared to the footprint of the flop at line number 25. So these flops usually FFs I prefer to use on the data path, where or combination of the registers. And down the line, I think modern EDA tools do register or flops combinations, and they have bigger cells. They combine multiple flops. So again, this is something to do with the physical design, but the key point to remember is that state flops prefer to have with the explicit reset, and the other flops on the data path, you may not need explicit reset. So set full cell footprint would be smaller, would save area and power. Okay. Although the reset in your design, which is feeded to the flops, that is synchronized with respect to the clock. Okay. The assertion is asynchronous, the assertion is synchronous. Okay. And then, it's a very simple line of code. You have, if the reset is asserted, you have the reset value. You can do reset value either 0 or 1, and then otherwise you have the input. All right. Now let's look at the arbitration function at line number 28. So that's the key part. You can define these functions, very helpful. So function will execute combinatorially in one clock cycle, right? So you know for sure in system Verilog that your code will generate combinatorial logic. Okay, so here we are saying that, okay, we get the request and we get the previous grant, means what was granted before in the previous cycle. So we take a decision on the previous grant. If the previous grant has given to the arbiter one location, then we create a mask variable that all other are allowed except the first, right? By default, everyone is allowed. Now, let's say if the previous grant was given to the previous grant variable came as second position, right? Then we know that the first one already was granted, but then we were feeding it to the flop. It'll get second position, but then the first two should not get an access. So our mask is getting updated that way. And then we kind of end with the request, right? Arbitration request, we end it with the request. And here we just do a priority encoder that if the 0th one is there, then we give a grant to the first one, second one, third one, fourth one, okay? And this is a default condition. Right? So this is a function. I will put that on my website as well. If there is an error or anything, let me know in your comments and feedback. I have compiled this code with Verilator program, which is a very good open source program you can install on your Linux machines, and it's a wonderful program. I'm just doing a lint check here, but again, it's compiling, there is no error or nothing, right? All right, so I would say that I leave it at this point, and let me know your comments, feedback on this. A very, very simple example. Another thing I would like to show here is that you may need a SIM file with the Verilator to execute if you want to build and execute, and that CPP file here it's a standard template. V stands for Verilator, HARV is your module name, and then this is standard Verilated header file, standard main line number 3, and then important is at line number 6. V stands for Verilator, HRARB your module name, pointer, and then HRARB, right? So this is a standard. You don't have to do too much. Just keep this file for compilation. And okay, now if I want to compile it Verilator, let me see what command I used before. Oh, sorry. Verilator -cc and same. Okay, so let's see. Does it do anything here? It compiled, seems like. Once it compiled, it will throw executable in the object directory. So it seems that it did create the CPP file, and it did not create the executable. To create an executable, I have to call the build. So let's see what happens now. Now it's going to create an executable file, right? Which you can just execute. You can write a test bench and execute the code. I did not develop a test bench here. As you can see here, it created a executable file. So if there is an error, syntax error or anything, it will not create. It created. You can run this code. Of course, I did not put any display statement or anything here, so it's not gonna display here anything. Okay. All right. Thank you very much, guys, for listening. I hope this is helpful for your learning. Leave your comments, message, or you can set up a online call for help.